I said, yeah, I have the equipment, but I need to take permission from all of you guys. I never expected anyone to say no. So I gave an open survey. There are 25 students, and one of them said, no, I do not allow it. So I couldn't do it. So it's always surprising as to we assume that, oh, how can someone say no? But we'll be surprised.
For the class, there is nothing else than that actual coursework. I think, I don't know, that one is somewhere if we just want to be different than other without reason.
But I have to accept that, right?
Yeah,
That's
definitely.
the point that yeah, we expect that everyone would agree, but then
Yeah,
in a
but
proper
this one, he should agree, but that
should,
class,
yeah, we should ask them.
yeah.
Let's hope that he says yes. As simple as he might be presenting stuff which he has not yet made a program out of. So then he might not want to. You never know what is. Yeah. So that's us. Yeah. Good. But let me know however you guys are proceeding, and if you're recording this, just one sentence is sufficient. There's a so that I'm aware.
Usually today I will be unavailable.
So yeah.
Tomorrow I have the same.
Huh?
Tomorrow I have the same, that's why I have to be here for the preparation.
Tomorrow you have what? I mean,
We have the same, it's a music festival.
oh yes, that's yeah. What do you say?
The same,
The sign.
yeah.
What do you say, Sunny?
The same.
Dasa? Dashara, yeah, yeah, that's how we are.
So all of you are invited tomorrow at
That's true.
11:30 AM in Evergreen Park, okay? We can celebrate, we can have food, fun, everything.
Where is this?
Evergreen Park.
Evergreen Park.
Yeah.
So 11:30 PM it begins and.
Yeah, it begins at 11:30
Okay.
AM, not the PM.
Yes.
And that would be at the night, also we'll do the barbecue party, but at the morning, it will be like a festival. We'll have a tikka and then like a chicken, mutton, all those things.
Evergreen Park, okay.
Yeah.
And this is Nepalese students doing it?
Yeah,
I'll try, yeah. I have a meeting until 12 or 1, so.
that should be okay.
Yeah, but don't assume that I'll come, my wife has to agree, so.
Okay. Or you can come with your family, that's okay.
Yeah, that's what, if I come, I'll come with.
Definitely.
Don't wait for me.
That's okay.
Yeah, good. Sania, where are you from? Can I ask? Yeah, that sorry. Okay. Oh. Does any one of you teach in this lab?
Dr. Salis, can we jump a little more?
Oh, are you guys? Oh. Yeah, and I have the autos focus also, right? Where are you guys seeing it? How do you know it is not correct?
If we could zoom a little more, then I think we should easily see the what is the problem.
It doesn't have,
Let me watch from here.
yeah, it doesn't have zoom abilities on the computer, the camera itself, you have to connect through an app.
Yes, that's what
And I don't remember.
try. And usually if I take away the autofocus, sometimes it does a good job.
If you write something, then
Yeah, let me connect to this first.
Makes very good.
Okay. Any better? I think so. Now it might be focusing.
I think first one, the bigger one is very much clear. Second one is it's like close. Third one is oh wow. Now that being even smaller will be clear now.
No, that we cannot do that.
Yeah.
Yeah, this
I
is the next one, this is discrete,
I think over here we can see everything.
but this, I will have very little board space, right?
Yeah.
Let's see, I mean,
Then it zoom out a little more.
yeah,
That one is the final one.
Oh, that will be, oh, okay.
but now it is clear, right? I changed the focus now. Change. Inlet. This is clear now, right?
Yeah.
If I write as big as the big.
Yeah, bigger is clear.
Yeah,
The
that is
smaller
the focus now
yeah,
is.
yeah.
correct.
The smaller is not
Yeah.
clear. Second one, we can go a little bit bigger than second
Yeah, I'll
one. it's
use
okay.
the first one,
Yeah.
but
Okay.
my tendency is to go smaller, so
Yeah.
you just have to
Okay,
tell me that, oh, it is getting small.
that's okay. We already have the note with us. That's why
No,
when
but
we see
stop
that,
me.
that's
Just
okay.
in between, just raise your hand or something, just make an action that
Okay.
reminds me that I'm
For
ready.
example, if with us today after the class,
Tell
in
it.
minute. For example,
Oh, yeah, Pooja, where is she? Yeah, 1, 2, 3, yeah, 6, you're missing 2, right?
you are missing. If they look
Yeah,
at video, then
told
they
you
may
he's
not.
not gonna be here today,
Did he?
cause he's off for a wedding in Colorado.
Oh, yeah, he did mention, yes. I almost thought it was you getting. So he's a bit, he's very
2
busy,
weeks, we need 2 weeks from today.
2 weeks from today.
I also won't be here, you know.
He also won't be here, are you not?
I think all of you guys should go for the wedding and I don't have the class.
It'll at least be us three going on Monday, I don't know about Friday.
And where is this? Is this in Carbondale or?
No, it's in like the Chattanooga, Tennessee area on the Tennessee-Georgia border.
Tennessee, Georgia. Oh, so it is, right,
It's about, yeah, it's about 6 hours.
6 hours then.
At least 6 or 7 hours.
But I think we don't have class in next Friday. For break,
That's correct. Fall break, we don't have a class.
next Friday.
And so
This, I mean,
when are you guys all missing the class?
It'll be
October
next,
17 and October 20.
October
Monday.
17 and October 20, Friday
and then Monday, coming Monday. Friday, we didn't have class.
No, October 17
and
is.
17 is 1 week from fall break, so 2 weeks from today.
Yeah.
So you'll miss Dustin's talk.
I will have to, yeah. Oh, yeah, you will stay. Yeah, cause he has to go pick Nate and Hannah up from the airport.
Is Dustin giving a seminar?
Well, again?
Dustin giving a seminar?
Yes. Yeah. But he will be there for a longer duration, about 1 week or so, so. You might get the info. Dustin was a grad student here,
Yeah,
he
that's
left
correct.
1 semester, yeah, some of you might. So even Rocky, you know, Dustin,
Yeah, I see, yeah.
you met him?
I think.
Oh, yeah, because you work in Bumsu's lab and he has visited Bumsu's lab, yes. Okay. Still we have camera problem?
No, I was just making sure I still host. Last time I wasn't host for some reason, it stopped recording after 40 minutes.
Yeah,
Alright.
this. Yeah, we have been. But. Plagued with. Problems with the camera this whole semester. Okay, let's see, 20 minutes down.
Yeah,
midterm two. That's October 31st. Friday. Oh, there was a discussion about this getting postponed. I think I noticed that most of you guys agreed on that. Right? So. Yeah, let me go through my emails and make sure that everyone of you guys agreed, and then we will move it by 1 week. I think if I, just based on the responses, I felt everyone. I think everyone agreed with that, I guess.
Yeah, so then it will go 1 week. Down November 7th. And homework 6. And there was I think at least I had a comment, probably it was Pradeep, you, that we should have a take home for the final exam. So that was a suggestion. But I should mention that the way it is going, it seems it may not be a take home. So it will be an actual exam, at least the way I see. So be prepared about that. And if there is a need for that, contact me separate.
Yeah.
But by default, I think it will be in class
For the
for final and midterm too. Things so. At the most, there might be one question take home, but most of it will be. Anything else, anyone? Okay, so we have been doing this very quick 1 week of mathematical techniques that is used in quantum mechanics. It is basically built on two ideas. One is idea of vector space, where how you project things and how the projections are measurement results, and we gave how probability is defined in a very generic scenario in quantum mechanics. And the second was the commutation relations that has a special meaning associated with dynamics. And here we want to do some few, at least 2 or 3 examples where commutation relations alone will be used for finding the dynamics or the derivative of a quantity. There is a similar thing that you do in classical mechanics. If you've done Poisson bracket, you can do pretty much exactly the same thing using Poisson bracket. If you've done classical mechanics here before, then you will see a direct connection between the two. But even otherwise, we will just think that these are the equations of motion, and or I shouldn't even say equations of motion. It's the definition of derivative in quantum mechanics, and we will see how it is operated on. So, so derivative alphas of dynamics, if you want. What do we mean by dynamics? Typically, we have a variable, like this is the Newtonian version or the classical version of a derivative, is that you have a variable lambda, then you have a function of lambda. Usually we think of this as a position, or this could be electric field, which depends on position and time. And then we are interested in derivative, which is defined as f by d lambda is equal to limit, let's say, delta lambda tends to 0 of the change in the function due to this lambda divided by lambda itself. You make a small change in a parameter, how does the function change? And the ratio of these two quantities is defined derivative. And using this, we can do a lot of things: velocity, acceleration, Newton's equations of motion. But we don't have to be in physics. It could be any model, right? If you're doing financial mathematics, stock prices are changing with time. or it could be some position, weather is position dependent quantity. We could pick any function and define a derivative associated with that, and then associate a model with that. In quantum mechanics, instead, what you do is that lambda is taken upgraded into another space, which is usually an operator. Think of it as matrices. These are called generators. The observer itself will be X. So these are called generators. Generator of lambda, let's say. Because still we want to think in terms of time, for example, or position. And this is the same quantity, any physical quantity. It could be stock prices for the bank, or velocity, or acceleration. But now these are matrices. There is no lambda dependency here. Like lambda dependencies, there is a mapping, if you want, from here to there. This is a position space. This is you usually say this is a Hilbert space. There is a mapping for every time there is a associated matrix in that space. That's the way to look at it. How do you define derivative then? Dx by lambda. You still want to talk in terms of lambda. How do you define the derivative? Then this is equal to, since we are doing quantum mechanics, it is IH bar. This is X comma G. So everything could be like have a feel for this being matrices, but this could be any set of operators. That's our idea. Right.
Yes, that's already generator, we have X age at stock price means.
Oh, what I meant was that if this is very abstract at this point, any function, right? If I have a variable, give me any function with respect to that variable, and I can define this. Let's say that function is the stock price. I want to use the word stock price instead of velocity and acceleration, because we don't associate physics with stock price, right? It is something very entirely different. And that's exactly my point, that if I have a function, usually based on data, I can see the stock price changing with time in a microsecond. Every microsecond you can see that. So if I have that data, then I can define my derivative. Right? If I have my function, I can define my derivative. It could be weather, like the temperature in Carbondale in every house. Like these days you have thermometers in every house. So it is possible to get the data from every house. I have a temperature. So temperature changes with position, not time. If I have that, then I might want to associate. Now I don't want to think of derivative with respect to lambda, but is there something else I can do? Can I associate a derivative with respect to an operator if you want? So lambda is upgraded in a sense. There is a one-to-one mapping from time, if you want, to a generator. Whatever you're interested in, could be stock price, but the easiest is velocity and acceleration. Velocity and acceleration become operators. That's what we do in quantum mechanics, right? Angular momentum here, which is a function of time, becomes an operator, right, which has no time dependence. Like spin has no time dependence in it. These are numbers. Right. That's what I mean. Is that clear? So some physical quantity here. So maybe you'll write this down. A physical quantity. So if I have a lot of variables, always I will have a lot of generators. But what are the most common generators that we associate dynamics with? One is time itself. So let me say lambda and G, right? So that's a generator. So this is in a normal space and time, and this is some operator space which we have to build, which is the construct. Usually this is done in Hamiltonian dynamics. This is what we do in classical mechanics. But most of us here have a reasonable idea of what a Hamiltonian is, what an angular momentum is, what linear momentum is. So if lambda is time, so this is t time. Usually the symmetry associated with is translation in time, then this is called a Hamiltonian, right? So this will be the h, which is the Hamiltonian. And I say just the time itself, but it is translation in time. Usually there is a symmetry that you talk about, there is a transformation, and this is uh, a generator associated with that transformation. Position. Again, you move the origin, you change the position of an object. It's called a translation in space. So let's say this is R. So I can have 3 dimensions. That's your R. And the generator associated with that is the linear momentum. Like here we're talking about what kind of changes do we make usually in physics. We make changes in time. This is called an evolution. So maybe this should be called evolution in time. And this is usually called a change in position or translation in position. But both are translations. Evolution is just a more colloquial word for translation in time. And that's associated with linear momentum. What exactly is the connection? Why do we associate this? That is more detailed. That is pretty much part of Noether's theorem. It's a whole discussion one can have in Lagrangian and Hamiltonian mechanics using the idea of action principle. But we won't discuss that. We will just say that this exists. We also talk about orientations, like things move around, right? So what if I rotate myself? How does the world look like? Like you're sleeping, you're looking at the stars currently in the north direction. Now, if you were to look at it in the south direction, how does the world look like? So if you rotate yourself, or that is equivalent to rotating the universe, how does the world look like? That's usually associated with the angle theta. So this is angle theta, which is a vector. Usually you need 3 vectors to orient your directions with. Often this is talked in terms of there is a direction of axis of rotation, and the magnitude of rotation. So any rotation can be thought of as 3 rotations, about 3 axes, but also as a single rotation about a single axis with a certain angle that you have. So again, that's idea of rotation and rotation transformation. So this will be the angles, orientation, let's say. For example, how does a magnet rotate? Like our Earth spins, right? So it is spinning. So that's orientation. So we talk about how does that orientation evolve in time, dynamics of rotation. That's associated with angular momentum. And there are 2 types of angular momentum, orbital and spin angular momentum. All that is included in this. So this is angular momentum. And these were there is how many, like 6 plus 1, 7. 7 transformation typically we associate with physical quantities. Like when we talk about dynamics, the word dynamics is a very generic usage in physics. We talk in terms of these 7 transformations. How does it evolve time? How does it translate in position? How does it change with position? How does it change with orientation? This was the case until about 120 years back, until Einstein came up. But Einstein showed us that even velocities matter, in which car you're sitting. If you're going on an interstate, in which car you're sitting and how fast you're going, that changes your perception. Like that's called relative velocity. So the relative velocity is also a parameter you can use to describe the world. And that's associated with the relative velocity itself, v. And this has a generator associated with it, which is called a boost operator. So this is the boost. This is less commonly seen in textbooks. That's primarily because it's reasonably new, like that's only 100 is, and one can do dynamics with any of these parameters. So here we will try to do primarily time is the easiest. So we will try to do examples associated with time, and angle theta, I will do at least one example and show how that works. Remember, we are not going to use this. The main difference we will use is I want to talk about dynamics, that means how things change with time, but not using our traditional derivative. We will use this derivative, right? So that's the basic idea. So let's take the simplest example of a ball drop under gravity, right? We never associate quantum mechanics to a ball drop on the surface of Earth, but we could say maybe on some planet on some microscopic planet, let us say, maybe a ball drop might have quantum effects. So that's a very extremely exotic example, but just so that we can have some connection with it because we understand gravity, let's see how it will look like in this space. So what is the Hamiltonian associated with a ball drop under gravity? So there will be, it's all, everything is happening in one direction, correct? Oh, did I become small? This is big enough, right? This we can, okay. So so there's an object with a mass m, and it's moving in z direction. Let's say this is z, right? And gravity is acting downwards, so that's your g. Everything is happening in the same direction, so plus or minus can take care of the vector nature of the system. And under gravity, it is just special. Only under gravity, it doesn't happen in electric field or magnetic field. Things become independent of the mass. Mass times acceleration is equal to mass times gravity. The mass cancels out. Only in gravity, it is very counterintuitive, but that cancellation creates this counterintuitive feature, which we take for granted, that a feather and a bowling ball drop in vacuum will fall at the same rate. We understand that. So what are the equations for this? Hamiltonian depends on z, so it's z direction, and it depends on the velocity in the z direction, or let me say momentum, right? Momentum in the z direction. So the idea is z is clear. Z is the height from some ground, and p is mass times dz by dt. And of course, here when I say this, the idea of derivative is inbuilt in, it seems like. That's because I wanted to associate this with the classical interpretation of a derivative. We don't know this, so let me just say this is just momentum, right? Momentum. Because I don't want to use that knowledge that it is mass times velocity. And this is Hamiltonian is associated with energy. There is kinetic energy and potential energy. Kinetic energy will be p squared over 2m, and the kinetic energy, potential energy of for gravity. How much is the potential energy for gravity? Sorry? mg z, right? Yes, that's right. So it is mgz, and here we have assumed that there is somewhere there is a ground, and z equal to 0 is the ground, and that it is 0. So that should be very clear. We understand this, I suppose, kinetic energy plus potential energy. That is all we use, and in fact, we don't assume anything about this being numbers. In fact, we say that these are operator, and to bring in the nature that these are operators, we will assume that these are quantum obey the quantum algebra of Heisenberg, right? Heisenberg's uncertainty relation. So let's say z comma p is equal to instead of saying IH bar, I'll put the IH bar on the left just to connect it with this. That's equal to 1. What is this equal to if I were to interpret in terms of this?
The change in position.
Change by
with
D.
respect to position.
Change in position, right? With respect to lambda for momentum is position. So derivative of z with respect to z is 1, right? Like we expect it to be 1. So in that it is consistent with this idea. Right? So derivative of position with respect to position. Why position? Because we are talking about momentum. This is a generator. Right? Generator momentum, what is it talking about? That's position. So this is basically a statement of partial derivative of z with respect to z itself. Right? So it's consistent with what we are talking about. Okay. So we want to talk about dynamics. Dynamics talks in terms of time, right? So we would like to talk about velocity first of all, how velocity changes and how acceleration changes. So velocity is dz by dt. So that will be the velocity of this mass that will come in. And we cannot use the traditional definition, we use this, right? So dz by dt would be equal to 1 over IH bar is equal to z, comma, g is now the generator of time. Generator of time is the Hamiltonian, which is available to us. I gave you that. So this is equal to the Hamiltonian. That's all. I can evaluate this in a way. So let's try this. So that's 1 over IH bar times z, comma, p squared over 2m plus mgc. Right? Wait. Now, let me simplify this. 1 over IH bar, 1 over 2m. Mass doesn't have any quantum features or operator features. It is only the generators and the physical quantity here. One can think of in some theory that mass has some features, but that's not what we are doing. We are only talking about z and p. So the dynamical variables here are z and p. That's what Hamiltonian does. So this is z, comma, p squared plus mg over IH bar times z, comma, z. When I wrote this down, z comma p is equal to 1, there is also this understanding that z comma z is equal to 0. I should also say 1 over IH bar. And here, since we don't have a position as a generator here, one can think of what will it be generators of. For that, we have to go into momentum space and talk about other physical quantities. Currently, I'm not doing that. We are restricting our analysis to just these simple generators, but we do know that any operator commutes with itself, right? So that's another way of looking at it. And at least in one dimension, it is not very obvious what will happen when z comma x comes in, right? That may not be obvious, but z comma z should be 0 just by definition of the commutator. But z comma x is not obvious, and that is what typically is exploited in some very microscopic. Microscopic is not the word. At a very fundamental level, when you say planet scale, these length scales might not be commuting with each other. So you do exploit that, but here at least z comma z in one direction, there is no issue with that. So then there is 1 over IH bar with p comma p, that also is 0. So when I say this, that's understood that that is also. So due to that reason, so this is equal to 0. Right, and z comma p, so the commutation relation distribution is there. Again, that is a property of a Lie algebra. Whenever you put in a commutation relation, there is a whole algebra of the commutation relation, but we have all taken some kind of quantum mechanics, you know how commutation relation distributes, so this distribution is given by 1/2m. Like you, whatever is then is coming as a product, write the product as P and Z comma P. Is this a familiar? And you say Z comma P times P. So what I've used here is A comma B comma C is equal to B times A comma C plus A comma B times C. That's a distribution property of commutation relation. Again, if you've taken a quantum mechanics course, you would see this in some form or the other. But once you have it in this form, it is clear that we can proceed and substitute Z comma P is equal to 1, and that comes with the IH bar. So this is equal to P over 2m, the first term, and in fact the second term is also P over 2m. So we have learned that the velocity is momentum divided by the mass, which is of course true. Classical mechanics, it's obvious, but this is not using classical mechanics, right? This is not coming from the simple idea of a derivative. This is coming from the idea of commutation relation. We have not used any idea of the traditional derivative, right? But it came out very nicely independent of that. And usually this is what happens, most of our ideas will remain the same. You won't learn anything new, but whenever it's a pure quantum system, like spin is a classic example, there things will be new. Like something that H bar comes in, that is a pure quantum system. Is that clear? Do you appreciate the new feature? So that's dz by dt. I can do the same thing. So let me. Where should I go? I think I can erase this part and. Can I go still here? Yes, right. Can go. Okay. So the next is the second dynamical variable usually is whatever Hamiltonian is dependent on, that's P. So right, dP by dt, but P I cannot. Yeah, I can, right? dP by dt, because anything with time I can do. This is equal to 1 over IH bar P comma Hamiltonian. If we do the same idea, 1 over IH bar P comma P squared over 2m plus mgz. It's well that is plus. Right. So P and P commute, so the first term will be 0, the commutation, and the second one will be P comma Z. So this will be mg times 1 over IH bar times P comma Z. And that we know, it was somewhere I erased that. That's a Heisenberg uncertainty relation, but with a negative sign, right? So it is Z comma P is what is 1. So this is minus mg, which is indeed true, right? This is the force, rate of change of momentum with time. Force is minus mg, right? That's the gravitational equation or Newton's gravitation equation. So we do get the both equations of motion using this. So for example, Newton's law will be time derivative, that is the acceleration, right? Mass times acceleration. But now we say P is m times dz by dt, right? dz by dt in a way. is equal to minus mg. That is exactly what Newton's second law is. That second derivative of position is accelerating. So it is consistent everything, but now we are doing usually more stuff, right? Like we want to solve the position as a function of time. And how do you solve for position as a function of time? What is the solution, by the way, when you drop a ball? Z as a function of time here? This ball? This is what you teach in your lab. What's the solution? So mass cancels out, so maybe the mass cancels out, right? Second derivative of z with dt squared. Now we're doing standard classical mechanics. Like z, let us say, is classical. Right? Simple position. What is the solution here?
GT squared.
Yeah, very good, right? So you would say z as a function of time. If you start from rest, it is minus half gt squared, right? With some z as a function of time. If there is an initial velocity, you would say there is an initial velocity v of 0 times t also. Right? That's your solution, right? But we would like to see, will there be any change? If there is quantum, what will be the change?
We didn't care about it.
So now we are on a microscopic planet. An electron is falling on a microscopic planet. How will this change? That's what you're asking. So where quantum features will be.
I think it's time independent after that.
It'll be time independent. So okay, we'll see. We'll try to solve it. But then we have to know how do we proceed, right? So usually, how did we get this? You wrote this equation, right? So then you have this solution. Then what do? Then you integrate, correct? The integration is a concept here, right? So we want to do something that does not use these ideas. So we want to now again do ZFT. We want to try this, but in using our operator formalism, we want to use these features and try to get that. So that's what we will do. Is the motivation clear?
Yeah.
Right. And again, whether it is in what system is this really applicable, I don't know. But it's at least meaningful to ask such a question that what are the quantum effects, if at all there are, for the simple system. Let me write this as P over M and use some board space, get some board space here. This I can erase now. And I also have dp by dt equal to I over h bar z no t. And that we said was minus mg. And mg itself is a constant, so g doesn't have any operator construct, right? So this commutes with everything else, right? So that's a like that's all. So, but I think all of you guys know this idea. Okay, so how do we go about? So we say that a function v of t, not in terms of the derivatives here, like we have the derivatives here, correct? In terms of these derivatives, we will say that any function can be expanded as a Taylor expansion, right? But in terms of these derivatives, not in the top derivative. So we will say this will be z of 0, right? Initial position plus time t times dz by dt evaluated at t equal to 0. Right, that's the Taylor expansion if you want. This is plus t squared over 2 factorial and second derivative of dz square p equal to 0 plus so on. We should control our tendency not to think of the classical idea of derivative. We want to use this derivative in terms of this, correct? So we would say this is equal, and I keep going higher derivative. So this is z of 0, which is technically an operator, right? Z position at time t is 0 plus time dz by dt is here, right? I know this commutation relation, so that's p over m. So this did not use the classical picture, so this is t equal to 0 plus dz by dt. How do I do this? Just to make sure that I'm not using classical ideas. So let me do this again. Second derivative of z with respect to time is the derivative of dz by dt. But dz by dt I already know is p by m. So that's equal to 1 over m dp by dt. Not using any of the classical ideas. That's dp by dt. But now dp by dt I know because of it's like iterative, right? Z is related to p and derivative of p is related to z. So dp by dt I know is minus mg, right? So this is minus g. What about the cube? Third derivative, because there are higher derivatives in here, right? So this is the cube over 3 factorial d cube z over dt cube and so on. And keep doing this. So let's go ahead and do dz cube, the third derivative. So that's the same as d by dt of the second derivative, which is minus g. And then we realize that, oh, that's a constant. Like we could talk about a situation where g itself has some quantum features in it, but we are not associate doing that. So in this case, this is equal to 0. Once this is 0, all higher derivatives will be 0, right? In fact, this will be dnz over dt raised to n is equal to 0 for n greater than or equal to 3. So this is second derivative exists. So this is d square over 2 factorial minus g evaluated at time t equal to 0. That's 0. So that's plus 0 and so on. So what we learn is that 0 plus t or p of 0 over m times t minus of gt squared. So this solution remains exactly the same even on a quantum planet, if I have to call that a quantum planet. So there was no change, remember, right? This was exactly what we did earlier. We wrote velocity, but velocity is momentum over mass. So does that mean there will be no quantum effects on this?
That leads.
No, it doesn't mean anything. Like we just said that our solutions are the same. But now, at least let me motivate what would happen. Let's think of remember what is Heisenberg uncertainty principle? X comma p not being equal to 1 instead of 0. What does that mean? Like at least at a physical level. Like as a derivative we saw, but what does that mean? There is some error associated. So there was a point mentioned that you can measure position, like that. This was an example we did last Monday also, that you can measure a physical quantity, and if the other physical quantity does not commute with it, like as a commutation relation, then this measurement will disturb the first one. So you measure, so if you want to do this exercise as an experiment, you need two quantities, z of 0 and t of 0, right? Velocity. So I want to first measure z of 0, oh, I'm going to drop it from this height. But then I have to say that, oh, I have to leave it with velocity 0. That's two information that is not compatible. If I allow that this is exactly at 3 meters, I really don't know about the momentum. I cannot make it precise enough. If I try to make this precise, this will get disturbed. If I make this precise, this will get disturbed. Is that clear what I mean? Like if I have to set some initial condition, I have to make a measurement. At least I need to know what is the initial condition. But that's not possible. Both together is not possible. One will disturb the other, which means that this experiment will start with an error, a huge error. Which means as you're going down, it won't stay along a line. I mean, if it was bifurcating in X and Y also, it won't stay in a line. But even in a straight line, if you say that we don't allow it in X, Y, its velocity will not obey this. There will be uncertainty in this piece. So how do we encode that? How you will say is that first of all, initial condition, z of 0. Uncertain. Okay, so let me talk about that. So when I say z of 0, so first thing is that z of 0 times p of 0 is not equal to 1. So this is the same uncertainty. So that's your IH bar. This implies that the variation, like let me make this better. So this is going to be delta p 0. So let's measure a quantity A, subtract the average out, square it, right? That will be called my error in A. That's a variance, right? What do we say? Like if there is an average of the class, and then I add all these quantities, and then I take a variation. Since I'm squaring this, it will always be greater than 0. Unless everyone has exactly the same average. So there is an AI in here, right? So it is sum over I, and then divide by, no, I think that's all that, and then divide by the total amount, right? That's your, so this is a measure of how much I'm deviating from the average. Right? If I drop this system for 10 10 or 1,000 experiments I do, how much do I deviate from my average? That's a measure of an uncertainty in A. So this commutation relation implies, again, this I'm not doing it here, I haven't motivated that, but in a normal quantum mechanics course, again, most of the textbook have this. You can start from here and show that this will be equal to, greater than, or equal to h bar, right? H bar over, yeah, just h bar, I guess. H bar over 2m, no, m is here. Yeah, velocity has the m. I think that's all that is, right? H bar over 2. Is that a 2? H bar 2. Okay. H bar over 2. Okay. Which means that you cannot make this precise enough. That's your initial conditions though, but you would like to know how much does you deviate, right? You started with an error that you didn't have a choice because you couldn't measure things. What about z of t? What you can talk about is how does z of t change as the beam moves? Like I have been motivating this with a gravity. A more realistic example is a beam of electrons, which is going down. Instead of gravity, you have electric field. Like that's uniform. So in an electric field, as the beam is moving, it will deviate from its initial or its direction in which it was moving. That will be called deviation, I suppose, right? Deviation of the beam or spread of the beam. I think it has to do with the spread, how much the beam will spread from the center point. And here, this will be equal to, like, if this was not equal to 0, we can show this, right? How much is this equal to? Z of t is equal to so much, so just calculate this. So this is equal to Z of 0 plus P of 0 over M times T minus half GT squared, comma Z of 0 itself. Z commutes with Z of 0. This is a constant, commutes with Z of 0, so there's P of 0 coming in. So this will be equal to there is a mass T over M. And then there is minus of IH bar. But the main idea here is that this uncertainty grows with time. So the uncertainty that we are talking about, del J of Z as a function of time. This is the spread of the object, not necessarily from the line, because X and Y we are not talking about. It is the error in the position itself, right? Is it behind or ahead? Like there are 10 people starting, but not everyone started from the same point. So that spread will go ahead, and if everyone was within 1 meter, as time evolves, they might be within 10 meters or 20 meters, right? That's what we are talking about. So delta of Z with respect to T times variation in Z with respect to time t equal to 0 will be greater than or equal to as a time distance. So this will be P over M and H bar over 2. In going from here to there, I'm using the idea of uncertainty relation, which I haven't motivated it exactly. That should be for completeness, one should have done that. I didn't do that. Is that clear? So that will be the quantum feature that will come up in this case. And this shows up in optics if you want to, electron beams are the best, where electron beams really deviate and one can try to quantify these things. Any questions on this? I'll do one more example, but I'll do very quickly the harmonic oscillator example, where like here we had this advantage that everything was 0 right here. So this was very simple example. It's the simplest example we do in classical mechanics also, right? So all this became 0, so the solution was very easy, right? So we'll do the classical mechanics, harmonic oscillator problem where that doesn't go to 0, and you see that a little more this mathematics coming in very. What I'm trying to emphasize is how derivative can be defined without the idea of the traditional derivative. That's the main idea. And then rest of it is physics and the interpretation that you need a whole quantum mechanics course for. Any questions here? So let's very quickly do the example of harmonic oscillator. Still one dimensional, so there will be a lot of advantage. Ease, simplicity in that. And since I have only 10 minutes, I'll make it quick also. Example, harmonic oscillator. The system is clear. It's a spring associated attached to a mass. So harmonic oscillator is X comma P. Right, a spring. So that's your mass M, spring constant K. Right, kinetic energy is still P square over M. 2M. That's the kinetic energy of this mass. There is no friction. And what is the potential energy of the spring?
Minus KX.
That's a force. Potential energy of a spring
K square.
of kx squared. Right? So this is plus of kx squared. Good, right? So, and it's convenient to define one more parameter in this, k over m, which is a characteristic frequency. The spring has a very specific frequency with which it oscillates. So that frequency we can call that omega. That comes out to be handy. Again, do the same idea, dx by dt, these are all operators, that's your 1 over IH bar, x comma Hamiltonian. Again, if you do the same idea, x commutes with x squared, the second term does not contribute. X comma p, it is the same algebra that goes through. This will come out to be p over m. And again, we have x comma p is equal to IH bar. That we are still using. Is that clear? I buried it here, but I think it should be fine. dp by dt is I over IH bar, and then we have p comma h, and this time the first term goes away. Two terms from here come in, p comma x, and p comma x is a negative because this is x comma p, and if you do it, this will come out to be minus kx, right? Force, rate of change of momentum will come out minus kx, right? Yeah, we need a quiz for today. Show this. Right. So that's just doing this commutation, completing that commutation relation. So x of t would be equal to x of 0 plus time t times dx by dt, 1 factorial, right? T equal to 0 plus t square over 2 factorial t square x over dt square equal to 0, and so on. Right. We keep going. First derivative we have done, second derivative, second t square x by dt square is equal to d by dt. Dx by dt is p, so this is 1 over, so d by dt of p over m. But that I know, dp by dt I've already done, right? So this is second derivative is dp by dt is x, right? So it is minus omega square times x. We're not using any classical physics, this is using this commutation relation, minus omega square x. Right? Third derivative, dt cube is equal to, so d by dt of x, so this is minus omega square dx by dt, but dx by dt I know is p over m, right? So it is minus omega square over m times p again. And you see that they are interchanging. First derivative as momentum, second derivative as position, third derivative as momentum, fourth derivative will have position, they will alternate. Right, we do one more, d4x by dt raised to 4, that's d by dt of d cube, which is dp by dt, and that is minus omega square over m, right? So yeah, and dp by dt is minus kx, so that's equal to omega raised to 4 times x. So if I collect these things together, if I collect all of them in x of t is equal to x of 0 plus t, and dx by dt, first one, dx by dt is p, right? So it's p of 0 over m plus t squared over 2 factorial. Second derivative now, second derivative is omega squared x, so that's minus omega square x times x of 0 plus t cubed over 3 factorial, and third derivative, that's here, minus omega squared over m times p of 0. And let me do one more so that pattern is very clear. fourth derivative is omega raised to 4 and x of 0. Collect there are two ways this comes about. So that is x of 0 times 1, and then there is minus omega t whole square over 2 factorial. So that's this term. And the fourth term is plus omega t raised to 4 over 4 factorial, and so on. You have plus e0, e of 0 over m, that is t, and that is minus of did I mess up here?
You cubed over 3 factorial.
3 factorial, yes, but what about this power?
And power will be.
So this was
Shouldn't be the third.
so this was omega squared. Oh, I think it's okay. Yeah, so it's fine, I guess. So I provide an omega. So let's write this as omega t cubed over omega. Right, and write this as omega t over omega. And the next one will be higher order. And there's a 3 factorial. I'll pull out an omega. And this you will be familiar. The series is cosine and that's sine. Right, so t of 0 m omega and sine omega t, which is exactly the solution for an harmonic oscillator. These are your arbitrary constants you would have got using initial using integration constants, but now we did not use integration. We did not use integration, notice. We used a derivative idea to solve a differential equation. So we solved a differential equation in the quantum in quantum mechanics. And then again, to what does this mean? You have to again do the commutation between x and x at time t with 0, x at time t with position, and how that physical system evolves, that we have to interpret. But this is the solution we have at this point, and then we have to interpret what that means. I'll stop here, pretty much good on time. Yeah, thank you.